All right, let's talk about something huge. I mean, we're talking about one of the most powerful and fundamental sets of rules in all of science. It's called thermodynamics, and it literally governs why anything in the universe happens at all. So yeah, let's dive right in.
And look, you don't have to take my word for it. Albert Einstein himself said that thermodynamics was the one theory he was convinced would never be overthrown. Its basic ideas were just unshakable. I mean, when Einstein calls something a sure thing, yeah, you're going to want to listen up.
Okay, so unbreakable laws. Big deal, right? Why does any of this actually matter to us? Well, because it holds the key to a really deep question. Why do some things just happen all by themselves while other things just don't? Think about it. An ice cube in your drink always melts. But have you ever seen the water in your glass just decide to freeze itself back into a perfect cube? Never happens, right? Why not?
And that's where thermodynamics comes in. At its core, it's this amazing predictive tool. It's almost like a cosmic detective, you know? It can look at any potential situation, a chemical reaction, something melting, a fire starting, and it can answer that one single ultimate question. Is this gonna happen on its own, spontaneously? Thermodynamics explains the why.
So, to get to the bottom of this cosmic mystery, like any good detective, we need our toolkit. We have to learn the lingo. Let's start with the absolute basics, just defining the scene of the crime, so to speak.
Okay, first piece of our kit, the system. And this is really just a fancy word for whatever part of the universe we've decided to focus on. It could be tiny, like a single living cell, or it could be something massive, like a whole car engine. It's just our zone of focus. Now, every system has to be separated from, well, everything else in the universe, right? We call that everything else the surroundings. And what separates them? The boundary. Think of a cup of coffee on your desk. The hot coffee is your system. The room is the surroundings. And the mug itself? That's the boundary. Simple as that. And you know, systems come in a few different flavors. You've got an open system, like a pot of boiling water on the stove. It's letting out heat and it's letting out steam. That's energy and matter. Then there's a closed system. Think of a sealed bottle of water. You can heat it up or cool it down so energy gets through, but the water's not going anywhere. And finally, an isolated system. This is like the perfect thermos, in theory. Nothing gets in, nothing gets out. The entire universe is pretty much the best example we have of an isolated system.
Okay, toolkit's packed. Let's start our investigation. What's our very first clue? And this one, it just kind of makes sense. It feels right. Things in nature, they seem to like to settle down, right? A ball rolls down a hill, not up it. It naturally ends up at the bottom, where it has the least amount of energy.
So in the world of thermodynamics, we have a name for this energy clue. It's called enthalpy. We use the symbol delta H. And a lot of things that happen all on their own are exothermic. That just means they release heat, so they have a negative delta H. Burning a log in the fireplace is the perfect example. It happens all by itself, and it gives off a ton of heat. The ash that's left over is way lower in energy. So it really seems like we're onto something. Maybe it's all about just losing energy.
But wait a second. Here's where the plot thickens. Is it really all about losing energy? Because if that were true, how do you explain an ice cube melting in a warm room? To melt, ice has to absorb heat from the air around it. It's taking energy in. And yet, it happens spontaneously every single time. So clearly, there's got to be another piece to this puzzle.
And that brings us to clue number 2. And this one, it's a little weirder, a little more mysterious. It turns out the universe isn't just pushed towards lower energy. It's also being pulled constantly towards, well, towards chaos.
There's a word for this idea, and it's one of the most important concepts in all of science: entropy. Entropy is basically a measure of randomness, of disorder. And let me put it this way. A clean room is orderly. There are only a few ways for it to be clean. But a messy room, oh, there are practically infinite ways for it to be messy. The universe just naturally drifts toward the outcome with the most possibilities. It favors the mess. That's the missing clue.
So here's where we are. We have these two huge forces pushing and pulling on everything. On one hand, you've got enthalpy, this drive to get to a lower, more stable energy state, to chill out. But on the other hand, you've got entropy, this unstoppable pull towards more mess, more chaos, more disorder. And any process that happens, it's the result of the epic battle between these two.
So, who wins? How do we figure out if the push for stability is stronger than the pull for chaos? Well, it turns out there is one single, beautiful equation that settles the argument once and for all.
And here it is.
This is the big reveal, the master key to the whole mystery. Gibbs free energy. The formula is delta G equals delta H minus T delta S. You see, it brings our two clues together, enthalpy and entropy, and it factors in temperature to give us a single final answer. This is the ultimate predictor.
And what's so amazing is that the answer it gives us is just so simple, so clean. If that final delta G number turns out to be negative, boom, the process will happen all by itself. It's spontaneous. If delta G is positive, nope, it's not going to happen on its own. And if delta G is exactly 0, then everything's perfectly balanced. We call that equilibrium. It's really that black and white.
Now this table, this really breaks down how that cosmic tug of war plays out. Look at that top row. A process releases energy, so delta H is negative, and it gets more chaotic, so delta S is positive. I mean, that's the best of both worlds, right? Delta G is always going to be negative. That process is good to go no matter what the temperature is. But what about our melting ice cube? That's the third row down. It absorbs energy, so delta H is positive, but it creates a ton more disorder when it turns into water, so delta S is also positive. So what's the tiebreaker? Temperature. When the temperature gets high enough that T times delta S part of the equation becomes huge, it overwhelms the delta H, and the whole delta J becomes negative, and poof, the ice melts. It's just so elegant.
So here's the bottom line, the big takeaway. By perfectly balancing that drive for lower energy against the universe's unstoppable march towards disorder, Gibbs free energy gives us this incredibly powerful crystal ball. It lets us look at basically anything and predict its direction. It answers that one simple question, will it happen, with the certainty of math.
Now, there's one little catch. Thermodynamics tells us if something will happen, but it doesn't tell us how fast it will happen. That's a whole other story. But just knowing what's possible and what's impossible, that's the foundation for, well, everything. So I'll leave you with this thought. If we have the rules to predict the very direction of the universe, what's the next great mystery we should point them at?